Alright, welcome to Fluids 101. Today we're going to be looking at kind of an introduction to fluids and what are fluids, just basic things regarding fluids. So let's first start off with the most basic thing. What exactly is a fluid? Now, a fluid is usually in the form of a gas or a liquid. Alright, so both of these are going to be defined as a fluid, and a fluid is also a substance that continuously deforms under shear stress. So if you don't know what shear stress is kind of like a tangential stress. So let's draw out an example here. So if we have this, we're gonna assume this to be a solid, and over here we're gonna assume this to be a fluid. So when we apply a shearing stress this way, it's gonna be, we're gonna see that our solid will deform to an extent, and after that the solid will kind of either return back to normal or it can permanently deform, right? So if we take a look at stress and strain, this is the stress strain curve. We're just going to make an imaginary curve. So strain is a measure of the deformity, and that is defined by the change in length over the original length, right? So stress, and something will look like that, and this was sometimes what you'll see for some materials, and you'll have the stress strain curve, and stress over strain, that's Young's modulus. So when we take a look at the solid, we can see those behaviors, that it deforms to an extent. I'm just going to get rid of that and that. But when we take a look at a fluid and we apply that same shearing stress, it will just continuously deform. Just keeps going. It'll continuously deform, right? Now, what exactly is the difference between a gas and a liquid in fluids? So a gas, kind of, when you place it into, let's draw out a little bucket or a little cup. We have these gas particles. They'll kind of go everywhere. They spread out. So these gas particles constantly spreading out like that. And when you have liquids, they have a more fixed volume, and you'll get kind of a free surface. So a free surface is a surface that's going to be perpendicular to the force of gravity, right? So you have your free surface. So when I break down these walls, or I put down part of this liquid is going to pour out through here, right? And that liquid is going to go on the ground, and it'll form kind of like this puddle thing, and it'll have a free surface. Now, what other behaviors differentiate the gas and this liquid? Now, gases are usually treated as incompressible, where gases are treated as compressible, well, liquids are treated as incompressible unless you get to certain conditions, certain extreme conditions. So what does it mean if gas is compressible? It means that density is not constant, versus both liquids and solids, our density is going to be constant, which means that we can have our volume changing for a fixed mass. And how do we actually describe this compressibility? Let's go ahead and derive that. So let's take a look at the relationship between pressure and volume, right? So compressibility is the property of the fluid where the fluid changes density or volume for a fixed mass under the application of pressure. So when we have our gas law, P1 V1 equals P2 V2, we can take a look at a kind of an inverse relationship here, right? One will go up, the other one will go down, right? And if we were to turn this into a differential, we would get change in volume over the change in pressure, and this would be actually negative. This derivative would be negative because we can see that we can see it right here, right? When your pressure goes up, your volume is going to go down. So this gives us the volume, the change in volume over the change in pressure, but we want this on a per unit basis. So in order to get that, we're just going to divide that by the volume, right? And because this is negative and we want it to be positive, we'll just throw in a negative sign over there. And this right here is the compressibility equation with constant temperature or entropy. So we'll label that beta, right? This is beta. And if we wanted to write this for density, again, I'm just going to use that same P1 V1 equals P2 V2. How do we relate volume to density? Well, we know that density, I'm gonna make that rho. It might be don't get it confused here. So volume is equal to mass per density. We're just gonna plug that in there. We'll get pressure is equal to mass over, I'm going to try to make it like this, rho. And remember that I said that we have a fixed mass, so that means that our mass is actually going to be constant. So we can take that out. Take a look at the relationship here. Unlike the previous relationship between pressure and volume, we're going to have a direct relationship between these two, and we get our equation, change in density divided by the change, or not divided by, over the change in pressure, and we're going to get that on the per unit basis, and this is already going to be positive. Alright, now let's take a look at, oh, what in the world? Okay, well, that's weird. Now, let's take a look at the velocity, right? So for a fluid continuum, we're not going to look at the actual, let me get rid of this as well too. We're not going to look at each fluid particle one by one. We're kind of, instead of tracking one particle, we're just going to track kind of like a location, stay in like a location and observe the motion of the fluid particles as they go past this location. So a way to think of this is like imagine being a cop, right? And you're just following somebody down the highway to get their speed versus sitting in one spot. So instead of just following somebody, you're just sitting in one spot and you're observing as they go past you. So that's kind of the approach that we're going to be using. And right, so in velocity, our velocity fields, we're going to define velocity with u, and u can be equal to u times, or u as a function of x and t, right? So we're going to have this continuum, this velocity field. We can define properties at points in space as well as time. But if the properties doesn't change with time, so let's say our property is this is our property right here, and if that's constant, meaning it doesn't change with time, then that's just equal to 0. So for steady flow, you'll see that there's not going to be a change in this property for a change in time because the flow is steady, right? So u here is also, we can also denote it in our vector, standard vector notation, right? So let's take a look at kind of the dimensions of the flow. So we always have 3-dimensional flow, right? But you'll see in most examples we put this in 1 or 2 dimensions just because it's easier to characterize the velocity field. These are only approximations. So if you'll see an example, something like this, the flow of fluid through a pipe with radius r, and you know your fluid is just moving down this pipe, right? You pretend this is the fluid. So when you have solid boundaries, you can have what's called no-slip conditions, meaning that there's 0 velocity at a wall. So the flow actually looks kind of like this. So no-slip conditions means that you have 0 velocity at the wall, and your fluid is actually going to kind of look like this, because you're going to have a shearing stress which arises due to the velocity gradient and difference in velocities throughout the fluid. So this is an example of flow through a pipe. And now let's take a look at something that relates to this, which is viscosity. Right, now viscosity is kind of an indicator of the amount of an indication of the amount of deformation that a liquid will undergo. A liquid will undergo under shearing strain. So Newton's law for viscosity says that fluid particles move in straight line. When fluid particles move in straight lines, the shear stress tangent to the direction is proportional to the rate of change. So this is going to be our shearing stress, and this is going to be our coefficient for viscosity. This is going to be equivalent to du. So we see if this is lower, our velocity will go up, right? So if we have something like water with a low viscosity, we'll have a higher velocity gradient. And if we have something like honey, which has a really high viscosity, then you'll see it exhibits a lower velocity gradient. So if we had a wall and we put water versus honey, then we obviously know that water would flow down way faster because of viscosity. So a fluid with low viscosity will exhibit a larger velocity gradient, a larger deformation rate. Sorry. So viscosity also has a stronger dependence on temperature than pressure. If you think about it, when you heat up something like honey or water, what will happen to it, right? So when you have as the temperature goes up, then your viscosity will go down for a liquid, but for a gas it will actually go up. So that's kind of it for fluids for the introductory video. I hope this helped clear stuff up for anybody if they need any help. And yeah, so this was the introduction to fluids. I hope you enjoyed the video.